Hello everyone. In the lecture series of Statistical Thermodynamics, we have so far learned about probabilities, distribution of particles, the concept of microstates and macrostates, then the classical distribution law or the Maxwell-Boltzmann distribution law, where the number of particles in the ith excited states was expressed as a function of the corresponding energy epsilon I, and later we have compared this Boltzmann distribution law with two more quantum statistics, which are the Bose-Einstein statistics and the Fermi-Dirac statistics. And finally, in the last lecture, we have derived the three forms of the barometric distribution law. So this chapter up to this discussion may be regarded as complete for the undergraduate students, and due to that we shall exclusively discuss some questions along with their answers here in this lecture only. So let's start with question number 1. Calculate the entropy of a system having 5 distinguishable particles at equilibrium with total energy 5 epsilon distributed in the energy levels with the energy spacing of epsilon. Okay, so remember the discussion at the very first lecture in this chapter, where 4 distinguishable particles were distributed in a system and the total energy was 4 epsilon. Now the total energy also increased and the number of particles also increased. So let's find out the macrostates first. Okay, these are the macrostates. So we have to try from the top level of energy, that means the 5th excited state. If we put one particle here, and before that one thing must be mentioned here, that first of all the particles are considered to be indistinguishable. Then the condition of distinguishability will be attributed, and then the probability W, thermodynamic probability, can be measured by using the simple formula. What was the formula? Now n factorial over product over I in I factorial. Okay, so let's try to find out the macrostates. So let's start from the top floor. Okay, here I am using the term floor and not energy levels. So if we use the term floor, it becomes more convenient to me to discuss. Okay, so in the top floor, any one of them, so 5 epsilon energy is only accommodated by this particle. So other rest 4 particles should be accommodated in the ground floor, and they will contribute no energy. So 5 plus 0 equals to 5. So our condition of 5 epsilon is fulfilled. Now after the top floor, only one possibility. Now in the 4th floor, move on to the 4th floor. So we have 4 epsilon of energy consumed, then only 1 epsilon is left in our hand. So we have to put one particle in the first excited state and the rest of the 3 in the ground state. Now in the 3rd excited state 1 and 2nd excited state 1. So 3 plus 2 equals to 5. Similarly 3 plus 1 plus 1 is also 5. Okay, so 3 plus 2 plus 0 plus 0 plus 0 is equal to 5. Similarly 3 plus 1 plus 1 plus 0 plus 0 is also equals to 5. Now on the top floor, 1 particle, 1 probability. On the top floor, 1 particle. On the 4th floor, 1 particle, 1 probability. But in the 3rd floor, 1 particle, there are 2 probabilities, isn't it? In the 2nd floor, 1, or in the 1st floor, 2 particles. Now if we keep the particle in the 2nd floor, that means the 2nd excited state, then there are 2 more probabilities. One, you put the rest of the particles 3 out of 4 in the 1st floor, then the overall energy should be 5 epsilon. Or you may put 2 particles in the 2nd floor and 1 particle in the 1st floor, and rest 2 in the ground floor. Okay, this will also constitute of 5 epsilon of energy. And finally move on to the 1st floor. You can accommodate all the 5 particles in the 1st floor. Okay, so these are the 7 number of macrostates where the probability can be calculated by using the formula n factorial over product over I in I factorial. So let us apply. That means if the particles are now distinguishable, then the maximum probability should be 5 for macrostate 1, and this way macrostate 4 and 6 would have 30, that is the highest number of microstates. So either microstate 4 or microstate 6, any one of them would be the most stable system or most stable state of this system. Okay, so now we have to calculate the entropy. So at equilibrium, W should be 30. So what should be the value of ln W? ln should be ln 30, and k ln W 1 into 3 into 10 to the minus 23 joule per Kelvin, and finally 4.69 into 10 to the minus 23 joule per Kelvin. So this is the entropy of the system at equilibrium. Okay, that's all for the first problem. Now move on to the second problem. Second problem is related to the barometric distribution law. At Earth's surface P0 equal to 1 atm, and at 10 km height from the Earth's surface P equals to half atm. So what is the value of P at 20 km height? So you are just doubling the altitude from 10 km to 20 km. So how do you do this? We have to do this by applying the barometric distribution law. So what is the barometric distribution law? Now the barometric distribution law is P equals to P0 exponential minus mgz by RT. So the value of P10, that means the value of P at 10 km height is half atmosphere. Okay, so this value is inserted here, and in place of P0 we have put 1 atm, and in place of Z we have inserted here 10 km height, so 10 mg by RT. So what is the value of e to the power minus 10 mg by RT? Now this is actually half. Okay, now for 20 km height, what should be the pressure? Now for 20 km height the pressure should be P20, and it will have the value P0 into minus mgz by RT, while Z would have the value minus 20. Z would have the value 20 km. So finally we shall get the value 1 into exponential minus 20 mg by RT. Okay, so what is minus 20 mg by RT? Actually this is the whole square of minus 10 mg by RT. So in place of that expression we can also write exponential minus 10 mg by RT whole square, isn't it? If you multiply this 2 with 10, then it would automatically become minus 20. And we know the value of exponential minus 10 mg by RT. This value is half. So half whole square atmosphere equal to 1 by 4 atmosphere. So this is the pressure at 20 km height. So that's all about the second problem. Now move on to the third problem. Third problem is little bit critical. In case of PR2, the vibrational energy levels have a constant spacing of 323 centimeter inverse at 25 degrees Celsius. Calculate the number of molecules in V equal to 1 state compared to the number in V equal to 0 state. Okay, so in order to do that we have to draw the energy levels. Okay, so we have two vibrational energy levels, V equals to 0, vibrational energy level 1, the ground state, and the vibrational energy level, the first excited state, where the level is V equals to 1. Okay, here the energy is 0 centimeter inverse, and here the energy is 323 centimeter inverse. Okay, and this energy level V0 equals to epsilon 0, and this V equals to 1 is equivalent to epsilon 1. The corresponding number of particles here consisting n0 particles, and here consisting n1 number of particles. So let's apply this number of n number of particles or n0 number of particles in the equation of the Boltzmann distribution law. So by putting this value we get for the first excited state n by f e to the power minus epsilon 1 by kt, and for the ground state n0 equals to n by f e to the power minus 0 by kt, because the energy is ground state, so energy should have 0 value, so it should be 0 by kt. So it is actually e to the power 0, that means 1. That means this expression is reduced to n by f. Okay, so what is the ratio now? Because compared, this term is written here compared to the number in V equal to 0 state. So simple, their ratio means this. right hand side part divided by this right hand side part. So n by f would be cancelled by n by f, only exponential minus epsilon 1 by kt would be left here. So the ratio n1 by n0 is right hand side divided by the right hand side, and this way it will get this expression. Now epsilon has the value, energy has the expression h nu, and nu is what? Nu is actually c by lambda. Now 1 by lambda is nu bar, that means the wave number. So it is 1 by lambda again is nu bar. So here we can write hc nu bar. So in place of h nu we can also write hc nu bar. That is why the energy term was given in the centimeter inverse unit, that means in the CGS unit, but in terms of wave number. Okay, so the expression of my epsilon should be written as hc nu bar by kt. Okay, so what are the values given for h or c or nu bar? Now h, the value of h is known to all of us. This is the Planck's constant, and it has the value in the CGS unit 6.626 into 10 to the power minus 26 erg per second. Okay, erg second, not per second, it is erg into second. Now here the value of c, the velocity of light, 3 into 10 to the power 10 centimeter per second. Okay, here the nu bar, look at the question, it is 323 centimeter inverse. So here 323 centimeter inverse. Then if you combine all of them, you will get the expression gram centimeter square per second square, that means erg. Okay, and the combined form of this calculation is 6.42 into 10 to the power minus 14, and the unit should be erg in the CGS unit of energy. Now what is the value of kt here? The denominator of the exponential power. So the value of kt should be first the value of k in CGS unit, and it is 1.38 into 10 to the minus 16 erg per Kelvin, and here it is 298 erg. Okay, 298 means 298 Kelvin. So erg per Kelvin into Kelvin equals to erg. So that is why here erg is written. So what is the multiplication? The multiplication is 4.11 into 10 to the power minus 14. So what should be the value of hc nu bar by kt? Now the value of hc nu bar by kt should be 6.42 into 10 to the power minus 4 divided by 4.11 into 10 to the power minus 14, and the result is 1.561. So the value of n1 by n0 should be exponential minus 1.561, that is 0.2099. That means the number of particles in the first excited state is 5 times less than in the number of particles in the ground states, isn't it? If there are 2 particles, then here are 10 particles. So the ratio is 2 by 10, it is 0.2, and accurately 0.2099. Okay, that means if you have 10,000 particles in the ground state, then you would have 2099 particles in the first excited state. Okay, so this is the ratio. Now let's move on to the fourth problem. What about the fourth problem? We have to prove if the number of particles distributed in equally spaced energy levels corresponding to Maxwell-Boltzmann statistics, they are in GP. This is very interesting fact. Really, the Maxwell-Boltzmann statistics is such a mathematical form where you would find that all the particles in the distributed in the different energy levels are in GP. Suppose in the ground state there are 1 million particles, and in the first excited state there are 0.1 million, that means 1 lakh particles. Okay, so in the ground state there are 1 million, 10 to the power 6, here are 10 to the power 5, then definitely this part would be consisting of 10 to the power 4 particles, that means 10,000. Okay, and in the third excited state, if it would have been present, then the number of particles should have been 1000. Okay, the 10 to the power 3. And next excited state 100, next 10, then finally 1. Okay, so this can be proved in the generalized form. Suppose we have 3 energy states number 0, ground state, then the first excited state and the second excited state. These energy levels have the names epsilon 0, epsilon 1 and epsilon 2 respectively, and the corresponding number of particles n0, n1 and n2 respectively. So the energy of the ground state equals to 0, the energy of the first excited state is epsilon, and the energy of the second excited state is twice epsilon. Okay, so what are the number of particles n0, n1 and n2? We have to find out the value by applying it in the Maxwell-Boltzmann distribution law. For the n2, it should be n by f e to the power minus epsilon 2 by kt. What is the value of epsilon 2? Now epsilon 2 has the value twice epsilon, so it has the final value n by f e to the power minus twice epsilon by kt. Okay, now n1, what is the value of n1? Now the value of n1 is n by f e to the power minus epsilon 1 by kt. What is the value of minus epsilon 1? Now the value of minus epsilon 1 is minus epsilon simply, so it is n by f e to the power minus epsilon by kt. And finally, what is the value of n0? Now the value of n0 is n by f e to the power minus 0 by kt, that is, it is overall 0, so it is 1, that means it is n by f. Now multiply this with this. Okay, what is the result? n0 into n2 equals to n by f into e to the power minus twice epsilon by kt. Okay, and this is nothing but n by f e to the power minus epsilon by kt whole squared. That means this is n1 whole square, and this is the law of the GP. Okay, so n0, n1 and n2 are in the geometric progression, or in short GP. That's all about the fourth problem. Now what is problem 5? Problem 5 is saying that consider a set of 3 equally spaced energy levels with a spacing 3 into 10 to the power minus 21 joule per molecule at 298.15 Kelvin. Calculate the total energy of an Avogadro number of the molecules distributed in these 3 energy levels. Okay, so this is the question. So what should be the answer? Answer is given here. The Avogadro number of particles n0, okay, and the particles in the ground state n0, n1 in the first state. N1 is the number of particles in the first excited state, and n2 is the number of particles in the second excited state. And the overall energy of the system is E, definitely the number of particles in the corresponding energy of the existing energy level. So if the energy level is epsilon 0 and the number of particles is n0 and epsilon 0, then their product n0 epsilon 0 is the overall energy of the first ground state. And similarly for the first excited state, the energy is n1 epsilon 1, and for the second one is n2 epsilon 2. Now we have epsilon 0 equals to 0 and epsilon 1 equals to 3 into 10 to the minus 21 joule. Okay, this is for particular one molecule. Okay, 3 into 10 to the minus 21, and definitely for epsilon 2 it should be just double of that. That means 2 into 3 into 10 to the minus 21 joule. That means 6 into minus 10 to the power minus 21 joule. Now let us find out the value of f. F has the expression sum over I exponential minus epsilon I by kt. Now we have 3 I expressions, that means 0, 1 and 2. If it is 0, then epsilon 0 is 0, so it is just 1, so it is 1, epsilon e to the power 0 equals to 1. Now if it is epsilon 1, then the value of epsilon 1 is epsilon, so it is simply e to the power minus epsilon by kt. And if it is epsilon 2, then it is twice epsilon. Okay, so in that case it should be e to the power minus twice epsilon by kt. So the final expression of f is 1 plus e to the power minus epsilon by kt plus e to the power minus twice epsilon by kt. Now the value of minus epsilon by kt we have to derive. Okay, so in order to do that we have to put the value of epsilon, then we have to divide by the Boltzmann constant and the temperature of the system. So these values are as usual. Epsilon has the value 3 into 10 to the minus 21, and the Boltzmann constant, these are all in the CGS unit. Okay, and Boltzmann constant 1.38, no sorry, this is in the SI unit, 3 into 10 to the minus 21. Let me check what was given. It is joule, so it was in the SI unit, not in the CGS unit. The previous problem was done in the CGS unit, but this one in the SI unit. So it should be minus 23. If it would have been CGS unit, then it would have been 10 to the minus 16, isn't it? So it is 1.38 into 10 to the minus 23 joule per Kelvin, and this is 298.15 Kelvin. So the result is minus 0.729. Okay, and this is definitely dimensionless, so no unit is given here, and the value of exponential power of this thing is e to the power minus epsilon by kt. Actually, e to the power minus 0.729. The value is 0.482. So what should be the value of minus twice epsilon by kt? Just double of this expression. There was a double of this value, minus 0.729 into 2, and it is minus 1.458, and its exponential power has the value 0.233. Okay, so the value of f can be found out like 1 plus the value of e to the power minus epsilon by k2 plus the value of e to the power minus twice epsilon by kt, and this, if we put these values, so the summation is 1.715. So this is the value of f. Okay, now the value of n0, n1 and n2. We have got the value of f, and we know the value of k, t and epsilon. So by the help of this epsilon, k and t, we can easily find the value of number of particles in the different energy levels, including the ground state. So the number of particles in the ground state, it is n by f e to the power minus 0 by kt. Now n is the total number of particles, which is actually the Avogadro number n0. So this has the value 6.023 into 10 to the power 23. In some books or somebody says it is 6.022. Both are correct. Okay. Achha. Now this is n by f, no problem, and we have got the value n by f 3.511 into 10 to the power 23. Okay. Just simply divide the value of the Avogadro number by f, what we have derived. So this is the result, isn't it? Now for this one, just n by f is simple one value, and e to the power minus epsilon by kt, this value also has been derived, and this way you can get the value 1.692 into 10 to the power 23, and n2 has the value, n by f has one value, and epsilon e to the power minus twice epsilon by kt, this one has another value. So product of these two, and this is resulting in 0.818 into 10 to the power 23. Okay, so these are the number of particles in the three shells. So what should be the overall energy of the system? Now n0 epsilon 0 plus n1 epsilon 1 plus n2 epsilon 2. So this is the expression of E when the values are incorporated here. But the energy of the first state, that means the ground state, is 0. So this is multiplied with 0. But the second one is not 0, it is 3 into 10 to the power minus 21 as given in the question. So it is multiplied with 3 into 10 to the minus 21, and this is the n1 value, and this is the value of n2, 0.818 into 10 to the power 23 into the value of what? Epsilon 2, that is twice epsilon, that means 6 into 10 to the power minus 21, and the overall value is in the unit joule, so it is 998.4 joule. Okay, this is the total energy, and that's all for the problem number 5. Now let's move on to the problem number 6. What is problem number 6? It's very simple. A system having 1000 number of classical particles has the following data. F partition function 1.582. It should not have any unit because it is dimensionless. E to the power minus epsilon 1 by kt equal to 0.368, and e to the power minus epsilon 3 by kt, that means the third excited state. Okay, corresponding to the third excited state. This value has 0.052. Okay, and also the values of n4 is given as 11 and n5 is given as 4. That is, the number of particles in the fourth excited state is 11 and the fifth excited state is 4. So we have to find out the values n0, n1, n3, and this Boltzmann factors. Okay, e to the power minus epsilon 4 by kt and e to the power minus epsilon 5 by kt. Simple. Just we know the value of f. So for n0 it should be n by f, because the exponential term is 1 because its power is 0, so it is simply n by f. Now the value of n is 1000 and the value of f is 1.582, so it is 632.1, but we have to, the number of particles cannot be a fraction, so we have to reduce it to the nearest whole number. So this is 632. Okay, The value of n1 is n by f into e to the power minus epsilon 1 by kt, and the value of epsilon 1 by kt is given. Okay, so just simply we have just derived the value of n by f. So n by f 632 into 0.368 equals to 232.5. so it has been to the nearest integral number 2. N3 has been determined by the help of Boltzmann distribution law. Similarly, n by f e to the power minus epsilon 3 by kt, the value of n by f is 632 as we have obtained it here, and e to the power minus epsilon 3 by kt, this value has been found to be 0.052. So the product of these two, 32.8, and the nearest integral is 33 integral number. Okay, and the value of e to the power minus epsilon 4 by kt and e to the power minus epsilon 5 by kt, very simple. Okay, just the formula, same formula, ni equal to n by f e to the power minus epsilon I by kt, and what should be the value of e to the power minus epsilon I by kt? Now it is ni into f by n. So here in case of 4, I equals to 4, it is n4 into f by n, and in case of 5 it is n5 into f by n. Okay, and we know the values are given here. The value of n4 is given to be 11, and the value of n5 is given to be 4. Okay, so 11 and 4, and the value of f has been found to be here 1.582. It has been given, it is not found, it has been given 1.582, and the value of n is also given, it is 1000. So this 1000 value. Okay, so simple, in a simple manner you can just calculate them and find the respective values. Okay, so we have got e to the power minus epsilon 4 by kt 0.0174, and e to the power minus epsilon 5 by kt is 0.0063. So that's all for the numerical problems from this chapter primarily, and we have so much more things to discuss. So that's all for today. Thank you. Have a nice day.